To better understand space and time, let's visualize an advanced civilization dominating not just worlds, but entire star systems. Engineers from this golden age, who knew no limits, dismantled planets and asteroids to build an intergalactic empire. But what happens when this apogee gives way to the twilight of their existence? In the vast emptiness of the universe, these cosmic giants knew that their end was near. The universe, in its inexorable march towards decline, leaves little room for hope. In the midst of a sky fading into eternal night, they found a final refuge, around a lonely, forgotten black hole. Now, imagine building a new home with the wreckage of demolished worlds, creating a shell to envelop the darkness. Within this fragile structure, they managed to survive, taking advantage of the dying light of the stars and the energy of the black hole, which, more than energy, gives them time. In a distant and aging universe, around a black hole, our civilization agonizes, watching the sky grow darker and darker. As the stars fade, energy becomes a supremely valuable commodity. And what is left for them but to wait? Every second is dedicated to survival, while tired eyes watch the inexorable advance of the heat death of the universe. What if we lived in a civilization where time, that concept that seems so fixed, could be shaped and stretched? Engineers in this society not only used, but mastered this malleable nature of space-time. Great portals distorting time and space allowed for incredible journeys across the empire, while the slow, ticking near gravitational pull of a black hole was used to stretch time. This allowed them to observe the end of everything. And speaking of time, it was Einstein's theory of relativity that revolutionized our understanding of space and time. Have we really come to understand it since then? Since the 4th century BC, philosophers such as Plato and Aristotle have debated a lot about space. Plato said that space was a medium in which everything exists, but without any qualities of its own. Aristotle agreed that an absolute void was impossible. However, it was only with the arrival of the 17th century and the maturing of modern science that we began to codify the processes of the universe into physical laws, migrating from myths to the language of mathematics. When Galileo was in his cabin on a ship with no windows and couldn't see the sea, only feel the movement of the waves, he realized something important about movement. Galileo concluded that if you are in an enclosed space and you are moving steadily and smoothly, like the rocking of a ship, you can't tell whether you are moving or standing still, unless you have some external reference point, like the view of the sea from the window. From this observation, Galileo began to develop the idea that movement is relative. This means that the movement of something can only be measured or felt in relation to something else. For example, you might think you are standing still on a train, but in relation to the train station, you are moving. This idea was revolutionary at the time and began to change the way we understand movement in the universe, being one of the first steps towards the development of more complex theories about movement and space, such as the theory of relativity that Albert Einstein formulated centuries later. And who could forget the clash between Newton and Leibniz? Newton saw space as an absolute, unchanging stage where cosmic changes took place. Leibniz, on the other hand, argued that space and time were meaningless without objects and movements to define them. Newton's view prevailed, influencing science for almost 2 centuries. But what if Leibniz was partly right? You've seen a cup fall off a table and shatter on the floor, right? But have you ever seen a cup pick itself up and jump back onto the table? I've never seen it, and I don't think you have either. Aristotle saw time as a mere interval between before and after, while Hindu philosophers saw it as an eternal cycle of creation and destruction. However, it was with the arrival of the Industrial Revolution that our battle with time took on a new chapter. How can you compare the work of a steam engine with that of a horse? This led us to the creation of thermodynamics. Did you know that the first machines operated at just 3% efficiency? Imagine the heat from the fire being lost in the air while the metal creaks, hot to the touch. In this context, the search for perfect efficiency proved to be an illusion. introducing the concept of entropy, a measure of disorder and decay. And then we reach the critical point proposed by Lord Kelvin, where a finite universe, following the known laws, is heading towards an inevitable thermal death. The stars fade away, one by one, leaving an old, dark, and exhausted universe. But what would happen if a little demon could separate hot atoms from cold ones, defying the laws of thermodynamics? This Maxwell's demon, as it is known, has sparked an intense debate about the relationship between energy, entropy, and information. In the midst of the apparent end, these thinkers revisit the great books of the cosmos. These ancient texts describe how space can bend and curve. And at the heart of these mysteries was light, a force so fast that it helped measure empires and set insurmountable limits. But what do we really know about the speed of light? The next time you look up at the sky on a summer's night, look for Vega, the brightest star in the north, located some 26 light-years away. Near the point of no return, it shines brightly, showing just how vast and mysterious our universe is. But now let's go back in time to 1676. Danish astronomer Ole Rømer made an intriguing observation while studying Jupiter's moons. He noticed that the predictions of the moon's eclipses became increasingly inaccurate and then corrected themselves over the course of the year. Why? Rømer realized that the variation was linked to the distance between the Earth and Jupiter, revealing something extraordinary. Light has a time to travel through space. This discovery challenged the idea of an infinite speed of light, setting it at an impressive 186,000 miles per second, an estimate not too far from what we know today. Einstein questioned why electricity and magnetism didn't fit into Galileo's relativity. This gave rise to the theory of special relativity, which tells us something surprising. No matter whether we're standing still or traveling at thousands of miles per hour, the speed of light is constant for everyone. But if this is true, what does it imply for space and time itself? This brings us to Minkowski's revolutionary concept of space-time, a union of the two that only makes sense when intertwined. And, as if that wasn't enough, Einstein didn't stop there. His general theory of relativity introduced a universe where space and time are not only bent by mass and energy, but are also flexible. In other words, in a black hole, where gravity is immense, time drags as you approach its dark heart. And how can we not mention the final proof of these theories that seem more like science fiction than reality? In 1971, an experiment with cesium clocks and jets that circled the Earth showed that yes, the movement and curvature of space-time can desynchronize time. Einstein was right once again. The universe doesn't just curve and rotate, it also expands. That's right. Every second there is more space in the universe than there was before. How can something grow without diluting? Although we usually think of space as something physical, something you can measure, move through, and where things exist, some theories suggest that space may not actually be a thing with physical properties of its own. Instead, these theories propose that space is a mathematical construct, a way we have created to describe relationships between objects and events. According to this view, space itself doesn't exist independently. It's just a model we use to understand how things are organized and how they interact. This means that if space really is just a mathematical construct, our understanding of the universe could also change radically. We would no longer be talking about a universe made up of things distributed in space, but of events and interactions that define space itself. This leads us to rethink many of the fundamental assumptions about how everything around us is organized and how it works. This perspective opens up new ways of understanding physics and cosmology, leading to new theories and discoveries about the nature of the universe. But here comes the big mystery. Without absolute time, how do we define a unique present? How can we tell where the past ends and the future begins? Within the equations of relativity, all pasts, presents, and futures are already written. Let's try to explain all this better. Think of two electrons approaching each other with their negative charges. They will repel each other until they stop and then move apart again. If we recorded this and showed it backwards, nothing would seem out of the ordinary. But why do the basic interactions of the universe seem to ignore the direction of time? And how is it that suddenly, on a large scale, time becomes so obvious? After all, you can't unscramble a scrambled egg, right? The universe, in the beginning, was born hot, dense, and strangely uniform, having an incredible property: low entropy, allowing gravity to act and form stars and galaxies. But how did this arrow of time emerge from so many interactions that apparently ignore time? Did you know that in a cemetery in Tallahassee, Florida, there is a tombstone with the name of a man who died in 1984 at the age of 82? That man was Paul Adrian Maurice Dirac, a British theoretical physicist who was born in 1902 and died in 1984. He is one of the most important figures in 20th century physics, especially known for his fundamental work in the development of quantum mechanics and quantum field theory. He stood out for his ability to use mathematics in new and powerful ways to solve physics problems. In 1928, he formulated the famous Dirac equation, which describes the behavior of electrons and predicts the existence of antimatter, a revolutionary discovery that was experimentally proven a few years later with the discovery of the positron. His work not only expanded our understanding of the subatomic world, but also helped pave the way for future theories and discoveries, including the development of elementary particles and the particle theory known as the Standard Model. He was awarded the Nobel Prize for Physics in 1933, shared with Erwin Schrödinger, for his contributions to atomic theory. Dirac knew that the equations of quantum mechanics needed to reflect Einstein's new views on space and time. This bothered him, and he worked hard to make the mathematics work. And then, in December 1927, the fog began to clear, revealing a relativistic quantum equation that explained the electron, its strange properties, and even antimatter. Today, quantum field theory, based on this mathematics, describes almost all fundamental particles and forces. But what about gravity? What if we included curved space-time in the Dirac equation? The last decade hasn't brought us much closer to this question, with theories such as string theory and loop quantum gravity offering fascinating but not yet definitive perspectives. What if space and time didn't really exist? What if they were emergent phenomena that we only perceive as macroscopic beings? Perhaps, after all, we are only just beginning to understand the cosmic stage on which we play out our existence. Do you have any idea what it would be like to live in this universe? Leave a comment. Don't forget to like and subscribe. Thanks for watching, and see you next time.